In our last video for this unit, we're going to look at domain, range, and continuity of our function graphs. So both our parent functions and just general in terms of how we can find domain, range, and describe continuity. So don't forget from your previous algebra classes, when you talked about domain and range for any function, your domain of a function is always going to be that complete set of possible input values. So in other words, it's all of the x's that you can plug into a function that are actually going to work with that function. So for example, your square root function, we cannot plug in negative x values because we can't take the square root of a negative number. Our range of a function is going to be all the possible outputs. So in other words, all of the y values that are kind of spit out of the function that in essence help make that function work too. Sometimes we'll look at things from the y perspectives, and sometimes we'll look at things from the x perspective. So both functions need to be, or both values need to exist for that function to work in whatever instance. So a lot of times we can actually describe domain and range and continuity of a function just by looking at what the graph looks like, what the picture is. And it just gives us another way that we can describe what the behavior of that function is going to be. So let's look at 4 examples as to how we can describe domain and range on these. And we are going to be using something called set notation. So again, this is something that you probably looked at briefly in algebra, but I'll explain it in detail in a little bit. But I want to show you first, how we can use that with these graphs. So our first function looks very familiar probably. So this is actually our quadratic or parabola function. But what happened to it? Where did it move from where the standard quadratic function would sit? Okay, so we would expect usually to have the point 0, 0, but if we think about the translations that we talked about earlier, the point we would expect to be at 0, 0 got moved down to the point 0, -3. And I'm actually going to go ahead and label that. And just to help us remember, because the more we write things out, the more we remember them, our function f of x, or you could use y equals, but I'm going to use very formal notation so you can see exactly how this might show up. That is going to be, well, x squared is our parabola, and what do we need to do to it to shift it down 3? We need to subtract 3 from it. Awesome. So our domain on this, we want to think about our x values. So again, x values kind of connected to our x-axis, which moves from left to right. So we want to think in terms of how far left can we go on our graph and how far right can we go. Well, if we look at the ends of the parabola, again, we don't actually have endpoints listed. And so we can kind of interpret this as the ends of these graphs are going to keep going on forever and ever, up and out. Well, if we're thinking x in terms of where are we moving left to right, in essence, our left piece of our graph just keeps going to the left and to the left and to the left, and it's just going to keep going forever and ever and ever. And same thing going towards the right, it's never going to stop. Yeah, the slope basically is going to get really, really steep as our x values that we plug in get bigger and bigger, but the graph itself keeps kind of flaring out. So that means we can use every single possible value. And so what kind of set of numbers do you think you could call this if we could use everything? So it's not whole numbers, it's not integers, it's not necessarily rationals. We can use every real number. And so the way that we write this in set notation is we're going to say we have this curly bracket. Our domain is our x values, and we want to use all of the x's such that, and that's what that kind of vertical bar means. It means x is such that x belongs or is part of the set of all real numbers. And again, I know this is a fancy notation. You don't necessarily need to write this fancy R with a double bar. If you just write a capital R, anyone who studied math will know exactly what you're talking about. But this is our formal way to say all real numbers in set notation. So again, to read it out formally, it really means x is such that x is in the set of all real numbers. Now our range, and again, if I'm using more formal notation, instead of writing y, I'm going to write f of x. So f of x is such that, and now we need to decide what y values or what our range values could be. So our x values, we could keep moving left and right and keep going on forever and ever. But is the same thing happening if we're going up and down? Well, I can keep going up on the ends of the graph. Again, they're going to keep going up and up and up forever and ever. But what happens when we get to that point 0, -3? We don't have anything occurring below that point. So that's basically the bottom end of our range. And again, if we're thinking about range, we're thinking about y values. So that means kind of the base of our range is at this -3, because again, y values for range. And then we're just going to keep increasing our y values from there, and they're just going to keep going on forever. It's never going to stop. So the way that we would express that is f of x is greater than or equal to -3. Now, the reason I'm saying greater than or equal to is because it does hit that point exactly on at 0, -3. And so you'll see what I'm referring to in a second. Okay, let's look at our second graph. So what function does this look like? This is our cubic function, and actually nothing happened to it. I still have my critical point of 0, 0, and 1, 1. And so nothing moved, nothing stretched, nothing shrank, no transformations were done on this function. So it's just a plain old f of x equals our cubic function, so x cubed. So that's just for a reminder. And so again, let's think about what's going on with the ends of this graph. So if I look at the top right of my graph, again, there's no distinct endpoint, so I can assume that this graph keeps going on, and it's going to keep going up and up and out and out. And it's the same thing with the bottom left piece of the graph. There are no stopping points on this graph. So it just keeps going out and over in both directions, and it's going to keep going on forever and ever. So if it's going to possibly never stop, that means I can use all of what kind of numbers? I can use all real numbers. So this is actually going to be all real numbers for both the domain and the range. So then how do you think you can write that in set notation? So we're going to kind of use our first one as almost our sample. The domain is the same as the first one. It's all real numbers for our x's. So x is such that x is in the set of all real numbers. And the only thing that changes with our range is instead of writing x, because domain deals with the x's, our range deals with y, or f of x. So f of x is such that f of x is in the set of all real numbers. The ends keep going left and right and never stop, so domain is all reals. The ends keep going up and down, so range is all reals. Okay, now graphs 3 and 4 look a little different. So these aren't a nice smooth curve. So with the parabola, even though it kind of stopped at -3, we still had this nice even curve, and it kept going, and we didn't have any stops, and we didn't have any kind of jumps or anything, a nice smooth curve. And same sort of thing with our x cubed graph, with our cubic function. It keeps going on forever and ever. Again, it's nice smooth curve. Yeah, it changes directions, but it still has points that exist anywhere you could try on that graph. Whereas number 3 is only distinct points. So we don't have anything going on in between any of these points. Let's go ahead and write down our coordinates just so we have them for reference. So our first point, again, I always want to think left to right, small to big. Our first point is at 1, 2. Our second point is at 2, 3. Our third point at 3, 2. And our fourth point at 4, 1. So we have very distinct values on this graph. So when we do our domain and range for this one, we're actually just going to list out those x coordinates and those y coordinates that exist on this function graph. So for our domain, and we're always starting domain the same way, curly bracket, x is such that. And then we have to describe these values. So I'm just going to list them out. So we have the numbers for our x's. We have 1, 2, 3, and 4. And technically, I'm actually going to update this to be very formal in my notation. I should use the x is such that it's in the set of 1, 2, 3, 4. But if you were just to list those out again, any mathematician would know exactly what you meant. You're saying x is such that it's in this list of numbers. Okay, for our f of x, for our y, for our range values, we're looking at all the y's, so the second coordinate on each point. So we're going to go f of x is such that f of x is in the set, and then we're just going to list out our numbers. So we have 2, we have 3. You could list the 2 again, but just for, keeping a smaller space, I'm not going to bother listing 2 again. And 1. Again, this is the only scenario where you would be listing out individual points. So I noticed as people were starting to list these out on some previous examples, especially on the pre-assessment, you want to keep in mind if you have a nice smooth curve, you should be describing kind of the overall scenario of what's going on rather than listing individual points. Because if you have all these in-between points, like for example on our cubic graph, where we have all these points that are kind of in between 0 and 1, we can't list each one of those points that are in there. There's actually an infinite number of points smushed into that very, very small thing, and we just don't have enough space to list every single number. So we have to give bigger picture of what's going on. Okay, so number 4 looks a little weird. So number 4 looks like he's a line, but he has this weird empty circle in the middle. And so if you think back to Algebra 1, you did a little bit of this when you were graphing inequalities. So sometimes you'd have like a segment that had an open circle on one end and a closed circle on the other. And so that was representing things that got kind of really, really close to that point, but they never quite hit it. And so when you see this sort of thing in a graph, it actually means that we're just missing that value. So this function is a little weird in that it's not defined at that point. And so the coordinates of this point are 2, 1. And both of those coordinates are going to be important because if our graph doesn't actually exist, we have an empty hole there, then that means we can't plug 2 into this function. And we're never going to get 1 out as an answer for a y on this function. It just does not exist at that point. So what's another way that you can say that something doesn't happen, that something isn't equal to a point? We're just going to say that our x can't be a specific value, or y can't be a specific value. So the way we do this for domain, again, x is such that, x is in the set of real numbers, but x does not equal 2. Because it can be every single other real number except for 2. Same thing for our domain, excuse me, for our range. So f of x is such that f of x is in the set of all real numbers, but it doesn't equal 1. So it's the entire set of real numbers except for 1, because we have a hole in that spot. And we're actually going to look at graphs throughout the year that do have holes or other discontinuities. And that's going to be an important thing to note. And we actually have some of those, or we do have some of those happening in our parent functions. So real quick before we look at those, just to define what does it mean when I'm pulling around these words continuous and discontinuous. So graphs 1 and 2 are continuous. They're nice and even. They have no gaps and no jumps. They have a nice smooth curve from beginning to end. But 3 and 4 are discontinuous because they have jumps. They have discrete points. They aren't connected. And for example 4, it had a jump or what we're going to be calling a hole. It literally has a hole in the graph where it just doesn't exist right at that point. Okay, and then the set notation that we were using, again, keep in mind they're are basically 3 ways, technically 4 ways we could do this. We could say all real numbers. So for example, we're going to, and we had this for our domain and our range, x is such that x is in the set of all real numbers. Or we could do that with our range as well. F of x is such that f of x is in the set of all real numbers. That means everything is fair game. You can plug any number in, you can get any number out. We could have something like domain is x value is greater than 1. So for that example, again, I would just use an inequality. So domain is what variable? That's your x, is such that x is greater than 1. Or we could do the very formal version, which I used above, which was x is such that x is in the set of real numbers, but x is greater than 1. Again, you can get as formal as you want. I'm going to tend towards using the more formal version, but most likely you're going to see this notation for that. Range is all y values less than or equal to 3. So that would be f of x is such that f of x is less than or equal to 3. And again, implied that that's your real numbers, you could include it to do very formal notation, or you can just write f of x is less than or equal to 3. So real quick, and you're probably going to need to pause on this as you're looking at your next page. So here's my next page. I want to go real quick through the parent graphs, and what I'm going to suggest doing is I'm going to look specifically at the ones that have kind of a different domain and range. So, and then I'm going to have you pause the video, fill in the rest of them, which are all going to be all real values, and then you can start the video up again and check that you filled those in correctly. So the ones that are going to be a little different, we have our constant. So our domain for our constant graph, which again is just a straight line, it's going to be y equals some number. So our domain, we can plug anything in. So that's going to be an x is such that x is in the set of all real numbers. But our range is very specific. When we have that horizontal line, that means that we're just going to get that one value out for our range. So we're going to be real specific on this one. F of x is such that f of x equals just that one number, whatever it is. This graph does not have any jumps or discontinuities or places where it doesn't exist. So this is a continuous graph. Okay, the next one that's not perfect is our absolute value. So again, that's y equals or f of x equals with our absolute value bars. Again, we can plug any x value in we want. The ends keep going on forever and ever. So domain, again, is all real numbers. But our range, we stop at 0, 0. So we're only going to use the numbers that are 0 and higher. So our range is going to be f of x is such that f of x is greater than or equal to 0, because it does hit that point down at the bottom. But again, even though it hits that point, it's still a continuous graph. We still have a smooth curve between all the rest of our points. We don't have any hiccups, so he is a continuous graph. Quadratic is actually exactly the same domain and range as our absolute value. So you can copy that over, and again, I'll have that for you to check in a second after I fill this out. Okay, next function, we're looking at our radical or a square root function. So again, can we use any negative values at all for our x's or our y's with our basic function that we see? Now, it can only use positive values, so our domain is x such that x is greater than or equal to 0. Again, you could do your formal notation, also have x is in the set of all real numbers where x is greater than or equal to 0. And our range is the same thing. So f of x is such that f of x greater than or equal to 0. Again, no jumps with the points that we have. So once we start our graph at 0, 0, we have a nice even curve. So because we have no jumps, we have no hiccups, he is a continuous. Okay. Cubic and cube root are another one that's going to have all real numbers. They keep going on in both directions forever and ever. So again, you can pause and fill those in a little bit. Okay, our next one is our rational or inverse graph. So again, that's f of x or y equals 1 over x. And here's the problem on this one. We don't have anything going on right smack in the middle of the graph. So we have our two separate branches that are kind of separated by x equals 0 in the middle and y equals 0 in the middle. Again, technically we have something called an asymptote. You don't really need to know that name yet, but we will talk about that when we get to our rational graphs unit. So that means we can use everything except for 0. So our domain, x is such that x is in the set of all real numbers, but x doesn't equal 1. Excuse me, 0. Same thing for our y values. So our range is f of x is such that f of x is in the set of real numbers, but it can't equal 0. It has a hiccup. So because it has that hiccup in the middle of the graph, this is a discontinuous graph. Okay. Our exponential and our logarithmic graphs, again, no hiccups. These are both continuous graphs, but our domain and range, both of them get really, really close to a number in one spot. So for our exponential graph, our domain, again, we can plug anything in. We can keep going to the left, we can keep going to the right. So domain is x such that x is in the set of all reals. But do we have anything happening below that x-axis? So that means our range, f of x, is everything bigger than 0. It doesn't actually hit the axis, so that's why I'm just using bigger than or greater than. I'm not using greater than or equal to. Logarithmic is kind of reversed on us. So I can't plug every x value in. You'll notice that that graph doesn't go past that y-axis. So it doesn't use any of the negative values. In fact, it doesn't even use 0. It gets really, really close to 0. It just never quite hits it. So our domain is x is such that x is greater than 0. Again, not equal to, just 0. Or just close to. But our range can be anything. Our graph can keep going down forever and ever, and while it's going to be a very slight increase, it is going to keep increasing as it goes up on the other side of the graph. So f of x is such that f of x belongs to the whole set of real numbers. Okay. Rather than pausing, again, what I want you to do is take a moment, fill in the rest of these. Every single one of the rest of these graphs that we didn't fill in are all going to have all real numbers for both the domain and the range. So go ahead, try filling those in, and then check against the filled in copy that I have posted right after this video. All right, as usual, again, please let me know if you have any questions. This marks the end of our unit. We are going to have a review day, so we'll have a review activity. I believe we have a Kahoot that we're going to do together on Zoom, and then you'll have the rest of the block to either work on the optional review problems that I gave you, or you can go back and retry any of the lesson checks that you still have an extra try on. So again, let me know if you have any questions. Thanks.